All right, this video we are taking a look at calculating square roots with and without variables inside the radical. Our usual plan, curricular outcomes review, our content. This time we are slipping in a bit of notes about technology use. So our curricular outcome. We want to demonstrate an understanding of factors of whole numbers by determining the square root in this case. So we'll take a look at perfect squares and prime factorizations. A perfect square is a number which can be written in the form of an integer multiplied by itself. So n squared equals s, n is an integer. Then s will be a perfect square. The name originates from geometry in ancient Greece. The measure of a 2D shape, like a square, was its area. The measure of a line was its length. So if you square a length, you will make a square whose sides have that length. So the conventional way to write the prime factorization of a number is with factors in ascending order and using exponents to represent repetitions. Again, that is merely convention. It is not technically incorrect to write them in other orders or to not use exponents, but sticking to conventions makes your work much easier to read and much more clear to the reader. And it's just far easier for them to work with the result. So there's not a great reason not to, which is why some teachers will even penalize if your answers do not follow the conventions. So negative numbers do not have square roots in the set of real numbers. They do in complex numbers, but that's not part of this course. An entire radical fits entirely under the radical, such as the square root of 48. So we'd call that an entire radical. A mixed radical has numbers both in and out of the radical, such as 4 root 3, which is another way to write the same value as the square root of 48. So when you're asked to fully simplify a radical, the goal is to write it, if possible, as a mixed radical, with no square factors left under the surd or the radical sign. So you wouldn't have root 12, because 12 has a factor of 4, but that would become 2 root 3, as we'll see in a moment. So algebraic square roots. Up to this point, you've probably been dealing with square roots only for numbers. Now we're going to add some polynomial factors, some algebra. From now on, do not use decimals in your answer unless the question gives explicit permission to do so. So we're going to be looking for exact answers unless you hear otherwise. That means if the answer is the square root of 2, you need to write square root of 2, not 1.414 and all the other digits on the display of your calculator. So you have to find the square roots of imperfect squares algebraically. Start with their prime factorizations. If a factor has an even exponent, you just divide that exponent by 2 when you take it out of the square root. And that factor will no longer be under the square root at all. So if you have, say, 5 to the 6 inside the square root, you'd have 5 to the 3 outside the square root. If a factor has an odd exponent, you take one and just set it aside, that will always stay under the square root, and then put half the remaining out. So if you have 5 to the 7, well, you're going to take one of those away. So you have like 5 to the 6 times 5. And when you bring the 5 to the 6 out, it becomes 5 cubed. So that's 5 cubed root 5, because that 7th 5 stays behind. So another explicit example here. If you have 54 x squared under your radical, well, 54 is 2 to the 1 and 3 cubed and x squared. 2 to the 1 is odd. There's no multiples of 2, so that stays put. 3 cubed, well, 3 squared. That 2 is less than 3, so we could pull 3 squared out, divide the 2 by 1, we get 3 to the 1 on the outside, and we leave behind that third 3 on the inside. X squared inside becomes x to the 1 outside. So now we have 3x times the square root of 6 when we multiply the 2 and 3 together inside. This is as simplified as we can make it. Let's do more examples. So the square root of 108. Well, we're going to start with our prime factorizations. 2 squared, that's even. That could come out. 3 cubed, we could pull the even piece out, the 3 squared, and leave our 3 to the 1 behind. Now we have all of our even exponents up front. We divide those exponents by 2 when we take them out. We leave our 3 to the 1 behind. So the square root of 108 is 6 root 3. Again, we write it as 6 root 3. We don't use our calculator's decimal approximation. Not unless you've been given explicit permission to do so, often in the form of being asked to answer to the nearest hundredth or thousandth or tenth, specifying some decimal place. Example 2, square root of 1,575 x cubed y squared. Well, the 1,575 part we have to factor. That's 3 squared, 5 squared times 7. We also have some x squared pulled out there, and leaving the x to the 1 behind. Now everything with the even exponents can come out. So that's 1, 3, 1, 5, 1x, and 1y come out. The odd exponents stay behind. That's our 7 and our third x. So that's 15xy times the square root of 7x. Example 3, 4,608 times w exponent 5. Well, we need to find the prime factorization of 4,608, but we can do that. We pull out enough 9s, we find it's 2 to the 9, we're left with 3 squared, and a w to the 5th. Now, we separate 1 out from each of our terms with odd exponents. So now our 2 to the 9 is 2 to the 8, 2 to the 1. 3 squared, the 2 is even, that's good. W to the 5th is now w to the 4th, w1. We pull our even exponent numbers out, divide those exponents by 2, and leave our odd exponents behind. And now we multiply 2 to the 4 and 3 and simplify. So 48 w squared times the square root of 2w. Some exercises. So find the square root of 16,428. Pause now to take whatever time you need. All right, this one does reduce to 74 root 3. Now, square root of 5,040 times s to the 9. Pause now, take whatever time you need. All right, this one simplifies to 12s to the 4th and root 35s. Third exercise, 79,475, x to the 7, y to the 4th. Pause now. Take whatever time you need. This is 85x cubed y squared root 11x. So, little note on technology here. TI calculators will only give the decimal approximations for the roots of imperfect squares. For example, the square root of 1,575, it just gives you 39.686269666. That's your calculator output. Casio graphing calculators by default will display the exact radical if they could find them in a lookup table. So it actually knows so many decimal places. If these are the decimals, it's probably a square root of 2 and so forth. There is an SD button to convert between the standard and decimal representation. The same is true with fractions. So on the Casio calculators, they would actually tell you the square root of 1,575 is 15 root 7, which is generally the preferred answer because it is the exact value. So Casios are not quite as user-friendly, not supported by all schools. Some will really insist on the TI, so their staff only have to learn one model. But this is one advantage they have in the tech. So in summary, a perfect square is a number whose square root is a rational number. Perfect squares, when written in their conventional prime factorizations, have only even exponents. There's two typos. I need to move the S from the first bullet to the second. But anyway, if a number's prime factorization has odd exponents, then it is not a perfect square and is a mixed radical when fully simplified. All right, if you have any questions, any feedback on this lesson, or requests for clarification or more examples of a certain type, let me know. I will try to respond in a timely fashion. Just post your questions in the comments.